Welcome back. In section 6.4, we'll be looking at the unit step function, also known as the Heaviside function, named after Oliver Heaviside, who first used it for analyzing the Laplace transform and engineering problems. And we'll also see how this unit step function can create switches, basically using continuous functions that we worked with before, but define a limited time interval over which they're being applied. So for example, if we want to look at a forcing function that's only applied over the first 2 seconds, we can turn it off. We can switch it off at that time. Or if we want to apply a forcing function where 2 different functions take turns, you can switch one on, then switch it off, and switch the other on. So back and forth. So this unit step function is really just a binary function. It's either 0 or it's 1. And it's 1 as long as t is bigger than c, and it's 0 as long as t is less than c. And sometimes you'll see this when c equals 0 as the unit step where t is less than 0 is 0 and t is greater than 0 is 1. Now you notice that there's no value given when t equals c. That's because, 1, we don't care for the integral what the value of it is at that point. 2, it's debatable what that value actually is. Is it 0, is it 1, or is it more likely 1/2? So we're not going to deal with the value at the point. We're only going to deal with the value in the 2 intervals. But just know that you can do either 0 or 1 or combination like 1/2 between them when it's necessary to decide that. First, let's graph it. C is a parameter, so it's a value of time. And leading up to that value, the function is 0, and then we jump up to 1. So there is our unit step function. Now let's look at the idea of switching a function on or off. So using unit steps to create switches. Let's start by drawing an example. Let's say we want to start off with 0. But we want to start off with a constant 1. And then at a certain time, let's say pi, we turn off this constant 1 and we turn on a sinusoidal function, which then turns off when it crosses, and then will stay zero. There's a graph of our f of t. So let's figure out how to describe it. Well, because our Laplace transform only cares about what happens to the function after time equals 0, we can start with this function being 1. And then at a certain time, pi, we turn off this function. So minus 1 times a unit step at t minus pi. Okay? And then at that same point in time, we turn on a sinusoidal function. Now the question is, what's the sinusoidal function that we turn on? It looks like it's a sine that just started right here at pi, but really we turn on a negative sine of t at t minus pi. So it's a sine of negative t. We just ignored it during the first wave, and then we turn it on when t equals pi. And then we turn it off when t equals, well, what would this point be? 2 pi, because it went down, back up, and over, and finishes. There's the full period of our sine of t, only it's negated. So we then subtract our negative sine of t, and now it's being turned off at t minus 2 pi. So there is a switching function. Now notice that you can also write this kind of switch function as a piecewise function. For all t less than pi, we can look at a value being 1, and we could say between 0 and pi, because we're never going to consider time before 0. The Laplace transform can't deal with it. So let's just say from 0 up to pi, the function is 1, and then it's turned off. And what's turned on is a minus sine of t for t between pi and 2 pi, and then 0 for t greater than 2 pi. So here we have 3 different perspectives on the same switch function, or combination of piecewise functions. Often you'll be given the function either in terms of a graph or in terms of piecewise function and asked to find out what is its definition in terms of the unit step. In each case, we start off with the activations, the initial function piece. We turn it off at the end time, we turn on the next piece. We turn that off at the end time, we turn on the next piece, and continue on and on.